All right, good morning. So let's get started. So let me just sort of do a quick review of what we did last week. Please, let's get started. Okay. So last week we actually sort of studied convex sets. Can we please start? So last time we studied actually convex sets. You know, we defined convex sets. A set is convex if whenever you have 2 points in that set and you join them by a line segment, the line segment also is contained in that set. So if that property is satisfied for every pair of points, then we say that we have a convex set. And then we proved that, you know, LP feasible regions are convex sets. And in particular, we also solved that LP feasible regions are very special convex sets. And we can actually use this property later on when we talk about algorithms. One last topic. So this is theorem number 3. So here's a statement. Every corner point of the feasible region of an LP problem is an optimal solution for some objective function. Okay. Now, what does this mean? So basically, we know that, you know, LP feasible regions have certain corner points. We know that it always has a finite number of corner points. So basically, what the statement says is the following. So for every corner point, I can find an objective function such that that corner point is optimal for that objective function. So let me try to illustrate by an example. So suppose that this is my feasible region. So just a very simple example. So how many corner points are there in this particular example? So there are 3 corner points, which are the corners of the triangle. Now, if I look at the statement, what it says is the following. So for each of these 3 corner points, I can find an objective function such that that corner point is an optimal solution for that objective function. So what does that mean? For instance, can somebody give me an example of an objective function for which this is an optimal solution? So think of this as the x1 axis. So one example would be if I want to maximize x1, then I want to move in this direction as much as I can. So this would be an optimal solution, basically, right? So for example, for this one, you know, maximize x1 would be an objective function for which this this corner point is an optimal solution, right? What about this one? Well, by the same reasoning. So instead, if I maximize x2, then this would be an objective function. An optimal solution for this objective function. What about this one? So I can find many examples, but for instance, I can find, you know, minimize x1 plus x2 would be an example where this point would be an optimal solution. So basically what this statement says is the following. So for every corner point in an LP feasible region, I can find an objective function such that that point is an optimal solution. Okay, so as a result, basically for every corner point rather, there exists an objective function for which that point is an optimal solution. Okay. So basically, this, you know, this kind of complements the earlier result that we had. So we said that if there is an optimal solution, then there's a corner point which is optimal. And this result says that for every corner point, there exists an objective function for which that corner point is optimal. Okay, it's kind of a complementary result. Does everybody see that? Okay. So essentially, as I said, you know, for every corner point, you can find at least one objective function for which that corner point is an optimal solution. Okay. So none of the corner points will be left out in this procedure, basically. For each one, you can find a corresponding objective function. Any questions about this? Is this clear? So is the statement and the example clear? All right. So now we're going to start discussing how to solve LP problems in general, okay? So far we have seen that if an LP problem has two variables, then we can actually solve it graphically, right? So we can draw the feasible region, then we draw the isoprofit line or the isocost line. But we also have seen examples in which, there are LP problems with more than two variables, right? So what are we going to do in that case? So that's exactly what we're going to discuss next. So this is, think of this as the second part of the course. So we're going to discuss the so-called the simplex method. So first of all, this is the name of the method, and simplex has nothing to do with simple, or simplex has nothing to do with complex either. So basically, it's a special term, okay? And I'm going to describe what it means later on in this course. So just think of this as the name of the method. So it has nothing to do with simple or complex or whatever. Or it's not a combination of simple and complex, okay? So this is just the name of the method. So we know from our earlier discussions that if an LP problem has a feasible region, or if the feasible region is non-empty, and if the feasible region contains a corner point, then we know that there exists at least one optimal solution, which is a corner point, right? So which basically means that, instead of looking at all possible feasible solutions, I might as well just look at corner points, basically, because if there's an optimal solution, then at least one of them will be optimal, right? So that's exactly the idea behind this algorithm. So first of all, I'm going to give you the conceptual algorithm. So, given an LP problem, so we're going to first start at given an LP problem that has corner points, so I should add that. Start at any feasible corner point. Step number 2 is move along the edge of this feasible region. Move along the edge of the feasible region. To an adjacent feasible corner point. Adjacent feasible corner point. With a better objective function value. And step number 3 is basically repeat step number 2. So repeat step 2 until no adjacent feasible corner point has a better objective function value. So it's a very simple algorithm, actually. At least the description is pretty simple. So given an LP problem, which of course should have corner points in order for this to work, we're going to start at any feasible corner point. So for now, we don't know actually how we can find that point, but suppose that somehow we find a feasible corner point. And then what I do is I look at the adjacent feasible corner points. And if there's a better one, then I'm going to move to that corner point. And I'm going to repeat this step until no adjacent feasible corner point has a better objective function value. Okay, so I'm going to give you an example. So just to make it easier, I'm going to just give you an example in 2 dimensions. So suppose that I want to maximize 2x1 plus x2 subject to x1 plus x2 is less than or equal to 1. X1 is less than or equal to 1, and x1 and x2 are both non-negative. So this LP problem has only 2 variables, and we know how to solve this problem, right? So we've seen this before. I'm just going to try to illustrate the idea of this algorithm on this simple example. So let's draw the feasible region. This is my x1 axis and x2 axis. So the first constraint looks like this one. The second constraint, sorry, let me just make it 2. So the first constraint is x1 plus x2 is less than or equal to 2 rather than 1. This is what the first constraint looks like. What about the second constraint? So x1 is less than or equal to 1. So first of all, I'm going to draw the vertical line, so which is given by this one. And then which side should I pick, left or right? I should pick left because the origin satisfies the inequality, so this is the correct side. Then we have non-negativity of x1 and x2. And if you think about this a little bit, the feasible region will be given by the shaded area, right? Okay. So how many corner points are there in this example? There are 4 of them. So we know how to solve this problem graphically, right? So what am I going to do? First of all, I'm going to look at the isoprofit line. So it goes through 0, 0 for 2x1 plus x2 equals 0. I need 1 more point. So if x1 is equal to 1, x2 should be minus 2, right? So as a result, it actually goes through somewhere over here as well. So that's a function that looks like this one. So this is my isoprofit line, x1 plus 2x2 equals, 2x1 plus x2 equals 0. So this is a maximization problem. Then I need to figure out what my c vector is. So what's the improving direction in this problem? So it's going to be given by the coefficients of x1 and x2. So I have 2, 1. So 2, 1 is the improving direction. So that looks like this vector right here. And note again that this vector is perpendicular to the isoprofit line. Now here's the idea of the algorithm. So first of all, it's going to, for example, start at this corner point. Okay, I'm going to call this corner point 1. And it's going to evaluate the objective function. So what's the value of the objective function at corner point 1? It's going to be 0, basically, right? So then it's going to look at the adjacent corner points. What's an adjacent corner point? So adjacent corner point is one that you can move along the feasible region. Okay, so for example, this one and this one are adjacent corner points, but this one and this one are not. Okay, so you can go from here to either this corner point or this corner point. And if you think about this a little bit, it's not too hard to see that both of them actually have better objective function values than this one, right? Because if I keep moving in this direction, then for example, here I will obtain a better objective function value. So as a result, suppose that the algorithm chooses this one. So next goes to this corner point. Okay, so what's the value of the objective function at the new corner point? So, you plug in 1, 0 into the objective function. So you get 2, basically, right? So the objective function value was 0. So now you have an improved objective function value of 2. This is a maximization problem. So now you just play the same game here. So I'm at this corner point right now. I'm going to look at the adjacent corner points. Well, there are 2 of them. I can go back, or I can go to this one right here. Okay. Well, if you think about this a little bit, going back does not really make sense, right? So you're not really making any improvement. So then you ask yourself, well, is this a better corner point than this one? Well, if you just draw the corresponding, isoprofit lines, it's not too hard to see that indeed this is the optimal solution. So the algorithm will move from 2 to 3. And that point is given by, I think, 1, 1, right? So the coordinates are given by 1, 1. What's the objective function value now? So now the objective function value increases up to 3, basically, right? Okay. So we started with an objective function value of 0. Then we have 2. Now we have 3. So I'm going to ask myself the same question again. So is there a better adjacent corner point? The answer is no, because if you look at this point right here, the objective function value is 2. If you look at this point right here, the objective function value is again equal to 2. Okay? So as a result, this is already better than any of the adjacent corner points. You stop and you say that this is the optimal solution, basically. Okay? So as I said, it's a very simple, at least conceptually, it's a very simple algorithm. Okay? So you just start with a corner point. You look at adjacent corner points. So once again, adjacent corner points are important. So this one and this one are adjacent. This one and this one are adjacent. But this one and this one are not adjacent. Okay? So you're not allowed to jump over in some sense. Okay? You're only allowed to move along the edges of the feasible region. Does that make sense? Okay? Is the idea clear? So it's a very simple algorithm indeed, right? At least, again, conceptually, it's a very simple algorithm. But the question is the following. So at least, in 2 dimensions, it seems like this idea will work, right? So basically you start at any corner point and then you move to a better corner point, better adjacent corner point, until you cannot find any more. But the question is, well, how can we generalize this? This idea to LP problems with an arbitrary number of decision variables. So at least, I mean, it seems like in 2 dimensions it works. The question is, what if I have 100 variables, for instance, okay? So how can I use this idea? Well, so if you just go back to this algorithm, so this is description. So in several places, I'm using the word corner point, right? So I'm starting at a corner point. Then I'm moving to an adjacent corner point with a better objective function value. And then for termination, I also look at if there are any better adjacent corner points or not. So which means that corner points are essential to this algorithm. So as a result, for a general LP problem, we need a characterization of a corner point, right? So in 2 dimensions, we know what corner points look like. But you know, what if I have 100 variables, right? So what do the corner points look like in such examples, in such an LP problem? So as a result, so we need a characterization of corner points for a general LP problem. So let me try to explain what I mean by that. So once again, in 2 dimensions, I mean, we know what the corner points look like, right? So they're given precisely by the intersection of 2 lines. And at least, I mean, by just looking at the picture, we know whether a given solution is a corner point or not, right? So now the question is the following. So suppose that I give you an LP problem with 100 variables, okay? And then I give you a feasible solution. Okay, so the problem is, of course, that you cannot really draw the feasible region in 100 dimensions, right? Okay, I mean, even in 3 dimensions, you know, it's getting already complicated. In 4 dimensions, you cannot draw it, basically. Okay, there's no way you can do it. 100 dimensions, you know, I cannot even imagine, basically. So the problem is the following. So if I give you a feasible solution, okay, any feasible solution, how can you tell whether it's a corner point or not? Okay. So now, unlike in 2 dimensions, we cannot visualize the feasible region. So we need a different characterization in some sense, okay? So we need to be able to say that, well, this point is a corner point, but this other feasible solution is not a corner point, for instance, okay? So we need to be able to characterize whether a given solution is a corner point or not, and that's exactly what we're going to discuss now. So, so we're going to try to give a more general definition of a corner point in some sense, okay? Is that clear? So, all right, so let me start with the definition. This is going to be important. An LP problem is said to be in standard form if all decision variables are non-negative, every constraint is an equality constraint, and the right-hand side of each equality constraint is non-negative. The right-hand side of each equality constraint is non-negative. So, given an LP problem, suppose that I give you an LP problem, I'm going to say that that LP problem is in standard form if it satisfies certain properties. So the first property is that all decision variables should be non-negative. Okay. The second property is that every constraint should be an equality constraint. Okay. And the third property is that the right-hand side of each equality constraint should be non-negative. Okay. I'm going to give you an example. So think of the following example. So suppose that I want to maximize x1 minus 2x2 plus x3, subject to, let's say, x1 plus x2 is equal to 4, and 2x2 minus x3 is equal to 2, for instance. And then I'm going to have x1 is greater than or equal to 0, x2 is greater than or equal to 0, and x3 is greater than or equal to 0. So the question is, would this LP be in standard form? Well, let's check the definition. So, there's no restriction about the objective function, so I skip the objective function. First of all, are all decision variables non-negative in that problem? Yes, so there are 3 decision variables, so all of them are non-negative. So the first property is satisfied, right? Is every constraint an equality constraint in that problem? Except for non-negativity, of course. Yes, so there are 2 constraints, and both of them are equality constraints, so the second property is also satisfied. Is the right-hand side of every equality constraint non-negative? Yes, that's also satisfied. So as a result, that would be an LP problem in standard form, okay? For example, let me look at this problem. Would this be a problem in standard form? So what property fails? So not every constraint is an equality constraint, basically, right? So this problem is not in standard form, but this problem is in standard form. So now you may wonder, well, what's the purpose of doing this, right? So why do we define a sort of particular form of an LP problem that we haven't seen before? Well, the reason is the following. So from now on, we're going to be always concerned with LP problems in standard form, okay? From now on, we're going to assume that the LP problem is already in standard form, okay? Now you may ask, well, not every LP problem is in standard form. So for example, that would be an example, and I'm going to fix that as well, okay? I'm going to actually show you that every LP problem can be turned into an equivalent LP problem in standard form. So standard form LP problems are quite general, basically, okay? So they can model every particular LP problem. So from now on, as I said, from now on, we will only work with LP problems in standard form. And of course, the natural question is why? Well, there are 2 actually important reasons. The first one is the following. If the feasible region is non-empty, if the feasible region of an LP problem in standard form is non-empty, then I make the following claim. Then it contains at least one corner point. Now, why is this true? So, why is it the case that if the feasible region of an LP problem in standard form is non-empty, then why does it necessarily have at least one corner point? We have seen this before. So what kind of LP problems have corner points? That's a question to you. So what kind of problems, LP problems, have corner points? The exam is next week, so what kind of LP problems have corner points?
Ones that contains a line.
Ones that do not contain a line, actually, right? So ones that do not contain, if the feasible region does not contain a line, then there's always a corner point, right? So we have seen this before. So how can I be sure that every LP problem in standard form actually has a corner point? Well, so remember, one of the properties that should be satisfied is that all decision variables should be non-negative, right? And if you recall, so a couple of weeks ago, we said that if the LP problem has the property that all waves are non-negative, then it cannot contain a line, right? Okay. Well, if it cannot contain a line, then there has to be a corner point, basically, right? So as a result, if I have an LP problem such as that one, for instance, I know that if the feasible region is non-empty, then there's always a corner point. Okay. So I guarantee that my LP problem in standard form always has a corner point. So that's good. Why is that good? Because my algorithm will work with corner points. Okay. So this necessarily guarantees that I will always have corner points for my problem. Does everybody see that? Okay. So this is the first property. The second property is the following. So every LP problem can be converted into an equivalent LP problem in standard form. So of course this is much more important in some sense, because what it says is the following. Even if your original LP problem is not in standard form, I can always convert it into another LP problem, another equivalent LP problem in standard form. So for instance, this problem is not in standard form, but I can always sort of convert it into an LP problem that will look like that one over there, okay? So I'm going to show you an example in a minute. But essentially, assuming that an LP problem is in standard form is quite general, basically, okay? Because every LP problem can be put into that form. Okay, I'm going to illustrate how to do that. So as a result, you can assume that every LP problem is in standard form. Okay? In other words, making that assumption does not restrict us. Okay, so because every LP problem can be turned into that form. And I'm going to show you how to do that. So here's an example. So suppose that I'm minimizing 3x1 plus 4x2 plus 5x3. Okay? So this is my objective function. I have 3 decision variables. Okay? And I have the following constraints. Let's say 2x1 minus x2 is less than or equal to 2. Then x1 plus x2 minus x3 is at least 6. And 2x1 plus x3 is equal to 4. And then I have x1 is non-negative, x2 is non-positive, and x3 has no sign restrictions. So x3 can be anything, for instance. So this is a perfectly fine example of an LP problem, right? So the objective function is in the correct form. All the constraints are in the correct form. So we have all sorts of constraints, basically. We have a non-negative variable. We have a non-positive variable. And we said that that's also possible, right? So x2, for example, can represent the loss, for instance. Okay, how much loss am I going to have? So that should be negative. And x3 has no restriction, so x3 can represent something like fluctuation, for instance. Deviation from a certain target can be positive or negative. Okay? So as a result, this is a perfectly fine example of an LP problem. The question is this LP problem in standard form? No, why not? Well, actually, it violates many properties, right? So not all the variables are non-negative. Okay? Not all the constraints. Sorry, this should be minus 4. Not all the constraints are equality constraints, and not every right-hand side is non-negative, basically, right? We have a negative right-hand side here. So as a result, this LP problem is not in standard form, right? So it violates many properties, basically. But what I'm going to do is the following. I'm going to start with this LP problem, okay? And I'm going to define another LP problem. And the other LP problem will be in standard form. And it's going to be an equivalent LP problem in the sense that, solving the other LP problem will also give us a solution to this problem. Okay, so we're going to try to do that now. So we will convert this LP problem into an equivalent, into a different but equivalent LP problem in standard form. Okay? So, what were the requirements of an LP problem in standard form? All decision variables should be non-negative, right? All the constraints should be equality constraints, and all the right-hand side values should be non-negative. So basically, I need to make sure that in my new LP problem, all of them will be satisfied. Okay? So let me start with the first constraint. So the first constraint is an inequality constraint. So 2x1 minus x2 is less than or equal to 2. And what I want to do is I want to actually turn this constraint into an equality constraint. Okay? And the question is, so how can I do that? So how can I turn this constraint into an equality constraint? Well, so if you think about this a little bit, essentially, you know, how would you read this relation? So the left-hand side can be equal to 2, or can be smaller than 2 as well, right? So I'm actually allowing both possibilities. So 2x1 minus x2 can be both equal to 2, or can be less than 2 as well, okay? So which means that if I look at the difference between the right-hand side and the left-hand side, so 2 minus the left-hand side, this expression, should be greater than or equal to 0, basically, right? So difference between the right-hand side and the left-hand side should be non-negative, okay? Well, so with that observation, what I'm going to do is I'm going to define a new variable for my problem, okay? And I'm going to call it, I'm going to use it to denote the difference between the right-hand side and left-hand side, okay? So in other words, I'm going to define S1 to be 2 minus 2x1 minus x2. Okay? So S1 is precisely the difference between the right-hand side and the left-hand side of my constraint. Okay? Well, so if this inequality is true, then what can I say about S1? Exactly. So S1 should be non-negative, right? So as a result, S1 should be greater than or equal to 0. Okay? Then I can rearrange this. So I can write this as, 2x1 minus x2 plus S1 is equal to 2. And I can also say that S1 is greater than or equal to 0. So basically, this constraint and these two constraints are equivalent to one another, right? If I satisfy this constraint, then I can also satisfy this constraint. And conversely, if I satisfy this constraint, then that means I also satisfy this constraint as well. Does everybody see that? So what's the point of doing this? Well, now I have an equality constraint, basically, right? So now, instead of having an inequality constraint, I turn this into an equality constraint. And the nice thing is that the new variable that I define is also non-negative. Okay, so that also satisfies the property of a standard form LP problem. So as a result, if you have a less than or equal to constraint, all you have to do is define a new variable, a new non-negative variable, and say that left-hand side plus this new variable is exactly equal to right-hand side. And this new variable should be non-negative. This basically means that the left-hand side cannot exceed the right-hand side, basically, okay? Because S1 is non-negative, so as a result, 2x1 minus x2 cannot be larger than 2. Okay? Otherwise, S1 cannot be non-negative. Does everyone see that? Okay? So as a result, we call S1 is the so-called slack variable. So then what I can do is I can sort of remove the first constraint and I can add these two constraints instead to my problem. Okay? And by doing that, I will have an equality constraint and a non-negative variable. Okay? Does everyone see that this constraint and these two relations are equivalent? So they're the same? Okay? All right, so now let me look at the second constraint. So what can I do about the second constraint? So x1 plus x2 minus x3 is less than or equal to 6. It's greater than or equal to 6, rather. So again, I want to turn this into an equivalent equality constraint. What can I do? Well, so now, in the previous example, my inequality was in the direction of less than or equal to. So which means that the difference between the right-hand side and left-hand sides That's my new variable, and that variable should be non-negative, right? Well, so now, how should I define my new decision variable in this case? So exactly. So now what I'm going to do is I'm going to look at the difference between the left-hand side and right-hand side, basically, right? Okay. So I'm going to define a new variable, and I'm going to call it to be the difference between the left-hand side and right-hand side, and that difference should be non-negative. Okay. So it's essentially the same idea. So what does this imply? So I'm going to define E1 to be x1 plus x2 minus x3 minus 6. And if the first inequality is satisfied, if the inequality number 2 is satisfied, then E1 should be non-negative, basically, right? Okay. So then what I can do is the following. So I can say that x1 plus x2 minus x3 minus E1 will be equal to 6. And E1 has to be non-negative. So essentially what I'm doing is I'm putting E1 on the right-hand side and I'm putting 6 on the left-hand side. And if I do this, then again I obtain an equality constraint at the expense of defining a new non-negative variable, of course, okay? So now E1 is a new decision variable. It should be non-negative. And once again, the last two conditions are essentially equivalent to this inequality, basically, okay? So if I satisfy these two conditions, then I'll satisfy this inequality. And conversely, if I satisfy this inequality, then I can find the value of E1 such that this is true, okay? All right, so just like S1, we call E1 is called the excess variable. So basically, E1 measures how much the left-hand side exceeds the right-hand side. Okay, so it's a measure of basically, what the difference between the left-hand side and the right-hand side is. Okay, if E1 is 0, then they're the same. But if E1 is positive, then the left-hand side is strictly larger than the right-hand side. Okay, so E1 basically measures how much the difference is between left-hand side and right-hand side. Okay, is that clear? So, any questions? All right, so what about the third constraint? Well, the third constraint is an equality constraint, but there's one problem that we have to fix. Okay, the right-hand side value is not non-negative, right? Okay, so what am I going to do? So how can I turn the last constraint into an equality constraint with a non-negative right-hand side? I can multiply by -1, basically, right? And that's exactly what I'm going to do. So 2x1 plus x3 is equal to -4 if and only if minus 2x1 minus x3 is equal to 4. Okay? So as a result, by just multiplying the third constraint by -1, I just make sure that the third constraint also satisfies the requirement that the right-hand side is non-negative, right? And since this is an equality constraint, I can multiply by anything that I want, right? So the equality will not be violated. So now we made sure that all the constraints are equality constraints. What is the extra requirement that we need to satisfy? Well, we need to make sure that all decision variables are also non-negative, right? So far, we don't satisfy that because x1 satisfies that, but x2 and x3 do not satisfy that. So we have to do something about that. Okay? So as I said, I mean, x1 is greater than or equal to 0, so there's nothing I need to do about that, so that already satisfies the requirement. So what about the non-positive variable? So how can I replace it by a non-negative variable? Exactly, that's exactly what I'm going to do. I'm going to define a new decision variable. And I'm going to call it x2 prime. And x2 prime will be exactly equal to minus x2. Okay? Now, if I know the value of x2, then obviously I know the value of x2 prime as well, right? And conversely, if I know the value of x2 prime, then I can get the value of x2. Okay? All right, so since x2 is non-negative, what does this imply about x2 prime? Well, x2 prime should be non-negative, basically, right? So as a result, now instead of having x2, I'm going to have minus x2 as my new decision variable. And since x2 is less than or equal to 0, minus x2 obviously should be greater than or equal to 0, basically, right? Okay, so instead of having x2 in my problem, then I'm going to replace every x2 by this expression, basically. Okay, so what I'm going to do is, so replace every occurrence of x2 in my problem by, well, what am I going to write instead of x2 from this relation? Minus x2 prime, right? So by essentially minus x2 prime. So if I go back to my problem, whenever I see x2, I'm going to replace it by minus x2 prime. Okay, so for example, the first constraint becomes 2x1 plus x2 prime then, right? So minus minus. The second one becomes x1 minus x2 prime, and so on and so forth. Okay, so that takes care of the x2 variable as well. What about x3? So how can I replace it by a non-negative variable? Okay. Well, so if I go into binary variables, then this is not going to be an LP problem, right? So as soon as I have binary variables, then it's an IP problem. So that's a different class of problems. So now we're still in the world of LP problems. Sorry? Okay. Well, but then you're changing the problem, right? So if you say that x3 should be non-negative, then that's a different problem. Yes?
We can say x3 is bigger than 0, and also define a new x3 prime, and that will be minus x3, and that will be larger than 0 also.
Well, you're close, but that doesn't quite work either. Okay. So here is the crucial observation. So any number, okay, any real number, whatever you can think of, can be written as a difference of two non-negative numbers. Okay? For instance, if I have something like minus 2, I can write this as 3 minus 5, for instance, right? Or if I have 7, then obviously I can write this, for example, as 10 minus 3. And if I have 0, then I can write it, I don't know, like 5 minus 5, for instance. Okay? So whatever real number you give me, I can always express it as the difference of two non-negative numbers. Okay? So what does that suggest? Well, I'm going to define two new variables now. I'm going to define x3 prime, which is a non-negative number. And I'm going to define x3 double prime, which is also a non-negative number. And I'm going to say that x3 is equal to x3 prime minus x3 double prime. So I claim that if I define these variables, then indeed x3 will be a free variable, basically, right? So there are no sign restrictions, because if x3 prime is larger than x3 double prime, then you're going to have a non-negative number. If x3 double prime is larger than x3 prime, then you're going to have a negative number, and so on and so forth. Okay? So basically, by doing this, I can express every free variable as difference of two non-negative variables. Okay? And by doing this, then I'm getting rid of this free variable. Okay? And instead, I'm having two new non-negative variables. Then just like we did in number 4, we're going to replace every occurrence of x3 in the original problem, in my problem, by x3 prime minus x3 double prime. So wherever I see x3, I'm going to simply write this expression instead. Okay? Does everybody understand this part? So is it clear that every real number can be expressed as difference of two non-negative numbers? Okay? And if you think about this, I mean, there are actually many ways of doing it, right? So you can express 2 as 2 minus 0, 3 minus 1, 4 minus 2, and so on and so forth. So there are actually several ways of doing the same thing. But the crucial thing is that every real number, regardless of its sign, it can be positive, negative, or 0, can always be written as the difference of two non-negative numbers. Okay? And as I said, if this is larger than this one, then you're going to have a non-negative number. If this is larger than this one, then you're going to have a negative number, basically, right? Okay? All right, so with these definitions, so now I'm going to write down the equivalent LP problem. LP problem in standard form. So what's my objective function for the new problem? So now essentially in the new problem, I'm going to use the new constraints, the new variables. In other words, I'm going to sort of remove all the, or I'm going to replace rather, all the constraints and variables that do not fit into the format, right format, okay? So let me start with the objective function. Remember, so x1 is unchanged, so as a result I'm going to use 3 times x1. Okay? What about x2? So instead of x2, I'm going to write minus x2 prime, so which means that I'm going to have minus 4 times x2 prime. And what about x3? So I'm going to write this difference instead of x3, so I'm going to have plus 5 times x3 prime minus 5 times x3 double prime. Okay? So what about the first constraint? Well, remember the first constraint, we replace it by these two requirements. So I'm going to have 2x1. x1 is the same. I have minus x2. What should I write instead? Plus x2 prime, basically. So I'm going to have plus x2 prime. Then I have plus s1, my slack variable, and the right-hand side value is equal to 2. So that takes care of the first constraint. What about the second one? Well, the second one, I'm going to replace it by those two expressions. Okay, I'm going to start with x1. Then I have plus x2. What am I going to write instead? Minus x2 prime, exactly. Then I have minus x3. What am I going to write instead? I'm going to replace it by this expression. So I'm going to have minus x3 prime plus x3 double prime, right? So I'm multiplying by minus 1. Okay. What else do I have? I have minus e1, and the right-hand side value is equal to 6. Okay? So what about the third constraint? Well, I'm going to start with minus 2x1. And instead of minus x3, what am I going to write? Again, I'm going to replace it by this difference. So I'm going to have minus x3 prime plus x3 double prime. And the right-hand side value is equal to 4. Okay? So what are my decision variables? Well, x1 stays as is. x1 should be non-negative. I have x2 prime, and that should be non-negative as well because of this restriction. Okay? Then I have x3 prime. That should also be non-negative. Then I have x3 double prime. That should also be non-negative. S1 is non-negative, and E1 is non-negative. Now, is the new LP problem in standard form? Yes, it is. So all the variables are non-negative. Okay? All the constraints are equality constraints, and all the right-hand side values are non-negative. So as a result, everything is satisfied. And the key observation is the following. So these two problems are equivalent in the sense that if I solve this problem, then, and if I have the optimal solution of this problem, then I can get the optimal solution of this problem as well. Okay? How can I do that? Well, whatever the value of x2 is, I'm going to multiply it by minus 1, and that will give me the value of x2 prime. And whatever the value of x3 is, I can always express it as the difference of two non-negative variables, so I can do that. And conversely, if I have an optimal solution of this problem, then I can always recover an optimal solution of this problem as well. So that's what I mean by equivalence of these two problems. So these two are not the same problems, okay? However, if I have a solution of one problem, then I can also obtain a solution of the other problem and vice versa, okay? In other words, there's a correspondence between every feasible solution in this problem and every feasible solution of the new problem. Okay, so they're not completely independent from one another. They're different problems. They're different because if you look at the first problem, there's only 3 decision variables, but in the second problem we have, I think, 6 decision variables. Okay, so as a result, the feasible regions, they actually live in different spaces, right? So this is a 3-dimensional feasible region. Over there we have a 6-dimensional feasible region. But there's a relationship between these 2 feasible regions. Okay, so for every solution here, I can find a solution in this region, and for every solution here, I can find a feasible solution in this region as well. Okay, any questions? Let's take a break. We'll continue.